From near-Earth space to the farthest known galaxies, this week has brought groundbreaking revelations in astronomy and space science. We begin our countdown in the outer solar system, where the planet Jupiter, often dubbed the vacuum cleaner of the solar system, has surprised astronomers yet again. This week, NASA's Juno spacecraft detected what appears to be a previously undocumented meteor shower in Jupiter's upper atmosphere. The discovery wasn't made through Juno's main science payload, but rather through its star-tracking navigation camera, called the Stellar Reference Unit. On July 16th, the instrument picked up faint, momentary flashes in the planet's cloud tops, flashes too fast and too irregular to be lightning. After extensive analysis, mission scientists concluded these were most likely the signatures of tiny meteoroids burning up as they entered Jupiter's upper atmosphere. This is a big deal. Meteor showers, those beautiful streaks we see on Earth, are common around our planet due to leftover debris from comets and asteroids. But seeing a meteor shower on Jupiter? That's new, and it could change how we understand the gravitational catch-and-hold behavior of the gas giant. According to Dr. Lucia Moreno, a planetary scientist with the European Space Agency, Jupiter's massive gravitational field doesn't just shape the orbits of moons and asteroids, it also likely accumulates stray particles over time. This discovery may help us study microdebris around the planet, material that's otherwise invisible to telescopes. There's a strong possibility that the meteors originated from the Trojan asteroids, ancient rocky bodies that co-orbit the Sun alongside Jupiter. If that's the case, it would be the first time we've seen material from these mysterious Trojans entering Jupiter's skies. Juno's orbit takes it close to Jupiter's poles and equator, allowing it to sample various longitudes and altitudes. Scientists are now scanning past data to see if they missed earlier flashes. They're also planning new observation sequences to capture more of these fleeting events on future flybys. From a space weather perspective, this opens new doors. Jupiter has one of the most complex and dynamic magnetospheres in the solar system. Adding a new variable, micrometeoroid entry, forces planetary scientists to revise existing atmospheric interaction models. And there's a visual poetry to this. While Earth's meteor showers are romanticized for their sky-gazing beauty, on Jupiter they're hidden, silent, and seen only through data. But the physics behind them remains universal. A cosmic body entering an atmosphere at high speed, colliding with particles, and producing light and heat, a stellar fingerprint of motion. So the next time you see a shooting star on Earth, know that Jupiter, 778 million kilometers away, is having its own version of a meteor light show. And now, for the first time in human history, we're able to witness it. Stay with us. Our next story brings us back to Earth, where a solar wind event gave us auroras in places you wouldn't expect, where space weather put on a spectacular show. On the night of July 18th, Earth's magnetosphere, our protective magnetic shield, was struck by a high-speed stream of solar wind traveling at over 700 kilometers per second. The event, classified as a G2 geomagnetic storm, was caused by a coronal hole that had opened up on the surface of the Sun, releasing streams of charged particles that raced across space. While such events are relatively common during heightened solar activity, what made this one unique was its reach. The auroras triggered by this storm were visible at unusually low latitudes, as far south as Colorado in the United States and parts of northern Germany. Social media lit up with vivid images of glowing greens and purples stretching across the sky, captivating photographers and stargazers alike. But while it may have looked beautiful from the ground, the impact in space was more intense. Satellite operators were placed on high alert as the sudden influx of solar particles can interfere with communications, navigation systems, and even power grids. Although no major outages were reported, several geosynchronous satellites had to briefly adjust orientation to minimize charging risks. According to NOAA's Space Weather Prediction Center, this is just the beginning. Solar activity is ramping up as we approach the peak of solar cycle 25, predicted to occur around mid-2025. And with that comes an increased risk of geomagnetic storms. Dr. Elena Harper, a solar physicist at NASA, explained, "The Sun operates on an 11-year cycle, and we're currently climbing towards solar maximum. That means more sunspots, more flares, more CMEs, and more chances to study how our star interacts with our planet." This week's solar wind was not associated with a coronal mass ejection, the more explosive type of solar outburst, but it still delivered enough energy to compress Earth's magnetosphere and produce vivid auroral displays. Instruments on board the GOES and ACE satellites recorded dramatic increases in solar proton and electron densities during the peak. What's especially exciting for scientists is the data collected during the storm. Ground-based magnetometers, auroral imagers, and low Earth orbit satellites all contributed to a global effort to monitor the storm's evolution. This provides a goldmine of information for modeling how Earth's magnetic field responds to solar variability. As solar activity continues to rise, so does our need to understand it. Not just to protect satellites and astronauts, but to better forecast the stunning auroras that remind us just how alive our sky really is. And if you were lucky enough to witness this week's lights in the sky, you were watching our planet's invisible shield come alive. Coming up next, the James Webb Space Telescope gives us another atmospheric breakthrough, this time revealing the fingerprints of water on a distant world. It's a milestone in exoplanet science. This week, the James Webb Space Telescope made one of its most striking atmospheric detections yet. Clear signatures of water vapor in the atmosphere of WASP-96b, a gas giant exoplanet located about 1,150 light-years away in the constellation Phoenix. The planet itself is uninhabitable, a hot Jupiter with scorching temperatures near 1,000 degrees Celsius and no solid surface. But what excites astronomers is not the possibility of life, but the confirmation that Webb's instruments can resolve the faint, telltale signs of chemical compounds in alien atmospheres, even from such immense distances. Using its near-infrared imager and slitless spectrograph, Webb analyzed the way light from the host star filtered through the planet's atmosphere during a transit. What emerged was a spectral fingerprint that clearly showed the absorption lines for H2O, water vapor. Dr. Amber Bryant, an exoplanet researcher at NASA Goddard, remarked, "What Webb is doing is not just detection, it's decoding. We're reading the atmospheric recipe of a world light-years away. This discovery marks a turning point in our ability to conduct comparative planetology beyond the solar system. On Earth, water is fundamental to life as we know it. Finding water vapor in exoplanet atmospheres helps us better understand how planets form, evolve, and possibly become habitable even when the planet in question is too extreme to support life." WASP-96b was previously thought to have a cloud-free atmosphere, but Webb's high-resolution data hints at the presence of haze, another layer of complexity in the planet's atmospheric structure. Clouds, hazes, and aerosols can alter our ability to measure chemical signatures, so detecting water even through such interference speaks volumes about the precision of Webb's instruments. The transit lasted about 6 hours, and every photon counted. Teams from NASA, ESA, and the Canadian Space Agency jointly processed the data, delivering one of the cleanest transmission spectra ever obtained for an exoplanet. While this single observation doesn't imply habitability, it proves Webb is ready for more ambitious targets, smaller, cooler planets with rocky surfaces where water could exist in liquid form, and that's exactly what scientists are aiming for in future observation cycles. Expect upcoming Webb campaigns to target TRAPPIST-1, LHS 1140, and even Proxima Centauri b, all promising worlds with more Earth-like properties. In the grand journey of answering the question, are we alone, this discovery is a small step forward, but a profoundly important one. The universe just got a bit more transparent. Still ahead, quantum entanglement goes cosmic as China pushes the frontier of secure space communication. This week, China made a giant leap in the quest for ultra-secure communication, and it happened in orbit. On July 22nd, researchers from the Chinese Academy of Sciences announced a successful satellite-based test of quantum key distribution, or QKD, between a ground station in Tibet and their quantum experiment satellite, MOSI, also known as Messius. This test is not only a technological triumph, but marks a profound moment where quantum physics steps into the realm of space infrastructure. QKD uses the principles of quantum entanglement, where two particles are linked such that the state of one instantly influences the state of the other, to create encryption keys that are fundamentally unhackable. Any attempt to eavesdrop on the communication would collapse the quantum state, alerting both parties to the presence of an intruder. In this latest experiment, photons entangled on Earth were beamed to the satellite, which relayed them over 1,200 kilometers. Despite the distances and atmospheric disturbances, the quantum signals remained intact, and the secure key was successfully generated. Dr. Jianwei Pan, China's leading quantum physicist, commented, "The dream of quantum-secure global communication is no longer theoretical. With each test, we're turning it into practical reality. What makes this breakthrough even more significant is its resilience. Space-based QKD has advantages over terrestrial fiber optic networks, where distance and signal loss are major challenges. In space, with low-noise optical paths and fast-moving satellites, global-scale quantum networks are theoretically more feasible. This success builds on previous QKD tests by China, but this week's trial involved multi-node relaying and ground-based quantum memory, key components for building a true quantum internet in space. If successful on a large scale, this could revolutionize everything from diplomatic communication to banking, space telemetry, and even data transfer between space agencies and telescopes. It also sparks international dialogue. While China leads the way, the European Union, the UK, and SAD are all investing in their own quantum space programs. The space race is no longer just about exploration, it's about information security in the quantum era. So, while most satellites beam down high-definition images or GPS signals, Mischius is whispering quantum secrets across the sky. Coming up, an asteroid discovered this week may pose a long-term threat. Here's what NASA and ESA are saying about it. An unexpected visitor has caught astronomers' attention this week, an asteroid, designated 2025 NT7, spotted by the Pan-STARRS Observatory in Hawaii. What's got researchers talking isn't its current location, but its projected trajectory over the next several decades. While there's no immediate danger, early orbital models suggest a small but non-zero chance of Earth impact late in the 22nd century. The object is estimated to be about 400 meters wide, large enough to cause regional devastation if it were ever to strike. That puts it in the category of potentially hazardous asteroid, or PHA. What's crucial to understand is that this isn't a cause for panic, but rather a reminder of how much we still need to track, catalog, and model the near-Earth environment. Astronomers have already scheduled follow-up observations using both ground-based radar and optical systems to refine the asteroid's orbit. Dr. Sonia Alvarez of the European Space Agency's Planetary Defense Office explained, "Asteroid NT7 is an excellent case study. It demonstrates how even a small uncertainty in position today can grow into large uncertainties a century from now. With more data, we can reduce that margin of error." The asteroid's orbital period is around 1.8 Earth years, and it follows an elongated path that crosses Earth's orbit. This type of orbit isn't uncommon, but when combined with the asteroid's size and speed, it makes precise tracking a top priority. In response to this discovery, NASA has added NZ7 to its Sentry Risk Table, a monitoring system designed to assess potential future Earth impact events. And ESA's FlyEye telescope, currently under construction in Sicily, will one day be part of the early detection network designed to spot such threats even sooner. This all comes just 2 years after NASA's DART mission successfully altered the orbit of another asteroid, Dimorphos, proving we can, in fact, nudge celestial bodies if needed. The global community is now discussing what combination of deflection, impact simulation, and data sharing will be needed for true planetary defense. For now, NT7 remains a cosmic curiosity, a reminder that the skies are full of moving parts, and that vigilance is key. It's not about fear, but foresight. Coming up next, a massive telescope on Earth, the Vera Rubin Observatory, begins early sky tests that may change how we map the night. A major milestone in ground-based astronomy this week, the Vera Rubin Observatory, nestled atop Cerro Pachón in Chile, has begun its first skycasts. Though still in the commissioning phase, the observatory's massive 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, has now officially taken its first images of the night sky. These early first light images might not be headline-grabbing beauty shots, but they are vital data. Engineers are calibrating optics, tracking mounts, and refining how the camera processes wide-field exposures. This telescope isn't about looking deep into a single patch of sky. It's about scanning the entire southern sky again and again, every few nights, for the next 10 years. That's the goal of the Legacy Survey of Space and Time, or LSST, a decade-long project that will generate a petabyte-scale dataset of the changing universe. We're talking about charting billions of galaxies, tracking near-Earth objects, measuring dark matter distribution, and even detecting supernovae in real time. Dr. Heather McAllister, a systems scientist on the project, said, "Rubin is a telescope that doesn't just see, it watches. We're moving from static sky maps to a living, breathing, dynamic universe." The observatory's mirror is over 8 meters wide, but what makes Rubin revolutionary is its speed and field of view. In one 30-second exposure, it can image an area 40 times the size of the full moon. It will do this night after night, building the most complete cinematic record of the sky ever attempted. Already, Rubin's sensors have captured trails of known asteroids, photometric variables, and calibration stars with remarkable clarity. These early tests are key for verifying data pipelines, ensuring that when full science operations begin in 2026, the observatory is ready to deliver its promise. In a landmark week for Indian space science, the Indian Space Research Organization, ISRO, successfully launched its Aditya L1 mission, the country's first dedicated solar observatory. The spacecraft, named after the Hindu sun god Aditya, was lofted aboard a PSLV rocket from Sriharikota and is now en route to the Lagrange Point 1, a gravitationally stable spot about 1.5 million kilometers from Earth. From there, it will continuously monitor the sun without the interruptions of Earth's shadow. The mission is packed with 7 advanced instruments designed to study various layers of the solar atmosphere, including the chromosphere and corona, and to track solar wind, magnetic storms, and coronal mass ejections. Its primary goal? To better understand how solar activity influences space weather and its cascading effects on Earth's satellites, power systems, and even human health. Dr. Meera Patel, lead scientist for Aditya L1's coronagraph instrument, noted, "With every solar eruption, we're reminded that the sun is not just a passive, glowing disk in the sky. It's a dynamic engine of radiation and plasma. This mission will help us map that behavior with unprecedented clarity." What makes Aditya L1 unique is its suite of synchronized instruments, some focused directly at the sun, others measuring in situ particles and magnetic fields, offering a holistic, multi-wavelength view of solar dynamics. Among its payloads is the Solar Ultraviolet Imaging Telescope, which will capture full-disk images of the sun in ultraviolet light, and the Visible Emission Line Coronagraph, which can monitor faint structures in the solar corona. This could improve early warning systems for geomagnetic storms, especially critical for countries with growing satellite constellations. India's entry into solar monitoring adds global strength to the network of sun-watching observatories that includes NASA's Parker Solar Probe and ESA Solar Orbiter. But unlike those high-cost missions, Aditya L1 is a testament to affordable, high-efficiency engineering and marks India's growing leadership in heliophysics. The spacecraft will take about 4 months to reach L1, after which science operations will begin. The data will be made available to researchers globally, expanding humanity's shared understanding of our star. With this launch, ISRO joins the select club of nations committed not just to reaching space, but to studying the forces that shape all space. Coming up next, we travel to the icy edges of the solar system, where a Kuiper Belt object has revealed something never seen before, a ring of dust far beyond Neptune. In a discovery that challenges our understanding of the frozen outskirts of the solar system, astronomers have detected a ring of dust encircling a distant Kuiper Belt object, 50,000 Quaoar. The finding, announced by a team using the European Space Agency's CHEOPS telescope and follow-up occultation data from Earth-based observatories, marks the first time a planetary ring has been observed so far from the Sun and around such a small body. Quaoar is a trans-Neptunian object, roughly half the size of Pluto, orbiting in the icy, distant Kuiper Belt beyond Neptune. What stunned researchers was the ring's location. It lies more than 4,000 kilometers from Quaoar, well outside the expected Roche limit, the boundary within which rings are typically gravitationally stable. This defies long-standing models. According to classical celestial mechanics, particles that drift beyond the Roche limit usually coalesce into moons. But this ring remains intact and dispersed, suggesting new forces or interactions may be at play. Dr. Pierre Vernazza of the Marseille Astrophysics Laboratory said, "This changes how we think about ring formation. It may be that fragile icy particles or thermal dynamics prevent the ring from clumping, or that Quaoar's own rotation plays a role." The discovery was made when Quaoar passed in front of a distant star, causing a brief dimming of light, a method known as stellar occultation. To their surprise, astronomers detected 2 subtle dips in brightness before and after the main event, consistent with a diffuse ring structure. What's more, this is not an isolated case. Earlier, similar rings were found around the centaurs Chariklo and Haumea, smaller bodies with unstable orbits between Jupiter and Neptune. The new find suggests that rings may be far more common in the outer solar system than previously believed. Some theories now suggest that micrometeoroid impacts, outgassing, or ancient collisions could create and sustain such dusty rings even in weak gravitational environments. While Quaoar's ring is not visible in telescopic images, its presence has been confirmed via repeated occultation signatures. Upcoming missions like the James Webb Space Telescope and next-gen ground-based observatories may soon resolve more details. For now, this discovery opens a new window into the evolutionary mechanics of small solar system bodies and serves as a reminder that even in the frigid darkness beyond Neptune, surprises still await. Coming up next, a star once thought stable suddenly dimmed, and astronomers are racing to explain why. Is it dust, an eclipse, or something stranger? An unusual dimming event from a distant star has sparked fresh intrigue among astronomers, reviving memories of the famous Tabby's star mystery. The object in question is HD 114762, a relatively bright F-type star located about 130 light-years from Earth in the constellation Coma Berenices. For the past decade, the star has appeared stable in brightness until now. Using data from the Transiting Exoplanet Survey satellite, researchers observed an unexpected drop in luminosity by nearly 5%, lasting more than 48 hours, far too long for a planetary transit and far too smooth to be caused by star spots. Dr. Niko Kovac, an astrophysicist at the Max Planck Institute for Astronomy, shared, "We've ruled out most of the usual suspects, eclipsing binaries, instrumental error, flares. What's left is something we don't fully understand yet." This has led to a surge of interest in alternative explanations. The most popular theory suggests a massive irregular dust cloud, possibly the remnants of a disintegrating exomoon or a swarm of asteroid debris temporarily crossed our line of sight. Interestingly, infrared observations from the Spitzer Space Telescope taken years earlier hinted at faint excess emissions around HD 114762, which could point to a dusty circumstellar environment. This new dimming event might confirm that the star is surrounded by complex material still evolving. Some more speculative interpretations recall Tabby's star, the infamous dimming star that sparked ideas ranging from comet swarms to alien megastructures. In that case, no clear answer emerged, but HD 114762 offers a new chance to apply more modern instruments and global observing networks. Follow-up observations are already underway using observatories in Chile, Spain, and the Canary Islands. Spectroscopic analysis may reveal if specific elements like carbon or silicon are absorbing starlight, helping determine the composition and source of the obscuring material. Events like this remind us that even stars we think we understand can behave in ways that surprise us, and that our models of stellar stability are always a work in progress. As astronomers continue to gather data, the mystery of HD 114762's dimming may soon be solved, or it may open a new chapter in our understanding of stellar evolution. And now, our #1 story this week takes us beyond science into history as we celebrate a major milestone in space exploration. July 20th marks one of the most defining moments in human history, the anniversary of Apollo 11's landing on the moon in 1969. This week, we remember Neil Armstrong's first steps, Buzz Aldrin's historic stroll, and the courage of Michael Collins, who orbited alone, and we reflect on how far we've come since that singular moment. In the 56 years since Apollo 11, the moon has remained both a symbol of achievement and a stepping stone toward the future. And now, the dream of returning, not just to visit, but to stay, is rapidly becoming reality. NASA's Artemis program, in partnership with international space agencies and private companies, is poised to return astronauts to the lunar surface by 2026. This time, the goals are broader, establishing a sustainable base camp near the lunar South Pole, conducting long-term scientific exploration, and preparing for future crewed missions to Mars. Just this week, NASA completed final testing of the Artemis II Orion capsule that will carry astronauts around the moon in a mission planned for next year. Meanwhile, construction of the Gateway, a lunar orbiting space station, is well underway, with components from ESA, JAXA, and CSA already entering fabrication. But the moon is not just America's destination. China, too, has ambitious lunar plans, having already landed robotic missions like Chang'e 4 and Chang'e 5. Beijing is working toward a crewed mission in the early 2030s and envisions a joint research base at the moon's south pole. India, after the success of Chandrayaan-3's soft landing at the South Pole, is collaborating with Japan on a new lunar rover. And Europe is developing robotic explorers to map resources such as frozen water. What's driving this renewed interest? The moon holds secrets of planetary history in its untouched regolith, and water ice trapped in shadowed craters could fuel future life support and rocket propellant systems. Beyond science, the moon is now a testbed for technologies that will be vital for Mars exploration: long-duration habitat systems, in-situ resource utilization, and deep space communication networks. As we commemorate Apollo 11, we also recognize that the new space age is not about one flag or one nation, but about building a multinational presence on the moon for the benefit of all humanity. 56 years ago, the world looked up at the moon and heard, "That's one small step for man, one giant leap for mankind." This week, we look forward to the next leap and the next horizon. This concludes our Skywatch Weekly Top 10 Countdown. Stay tuned for a recap and next week's cosmic stories right here on Anantum and beyond. Stay tuned for next week's cosmic stories right here on Anantum and beyond.